that's not what you're going to test this on.
Because on a note card, all it is taking a carboxylic acid reacting said carboxylic acid with bromine, Pdr3, and I chose this particular example because if you were now to take this and treat it with ammonia to do the SO2 reaction, the product would be phenylalanine. Is one of the 20 common amino acids. And you'll notice that I drew this as a bitter ion because the carboxylic acid hydrogen is much more acidic than the ammonium hydrogen. In solution, the amino acids exist with a negative charge on the carboxylate oxygen, a positive charge on the ammonium. Right? So, very simple, right? Carboxylic acid, bromine and Pdr3 makes the alpha bromo carboxylic acid. There are 4 distinct stages to this reaction. In stage 1, we convert the carboxylic acid to the acid bromide. So the net reaction in this stage 1 take the carboxylic acid and make acid bromide using Pdr3. Right? And I didn't actually go over the mechanism for how to make an acid bromide from a carboxylic acid Pdr3 because I knew that we would be doing it as part of the Hell-Vollhard-Zelinsky reaction. Phase 2 is the alpha bromination, takes back acid bromide, and puts some bromine. Sorry, that's stage 3. Stage 3.
Wait, where's stage 2?
Yeah, we're going to put stage 2 up there. Cut it down. Stage 2 is to make the enol. Tautomerization. So stage 2 takes that acid bromide and makes the enol product. Stage 3 is to brominate that. To make the alpha bromo compound. And then stage 4 is to do a bromine hydroxide exchange where the alpha bromo acid bromide reacts with the regular carboxylic acid to regenerate that. So you're basically taking this bromine and that OH group and exchanging them. Right, so the bromide ends up over on this carbon and the OH ends up on that carbon. And the reason this works is this is a more reactive acid bromide. And this is a less reactive acid bromide. It's actually identical to the reason this one works, where Pdr3 is the more reactive acid bromide. And the carboxylic acid bromide is the less reactive acid bromide. So if you think of the reaction as going in these 4 stages, conversion of a carboxylic acid to an acid bromide, tautomerism, right, converting of the keto tautomer to the enol tautomer of that acid bromide, bromination of the enol, and then the bromine hydroxide exchange. It's a little easier to get each of those steps. So these 2 steps, keto-enol tautomerism and bromination of the enol, are pretty straightforward, and you should be able to do those mechanisms. The Pdr3 mechanism is somewhat analogous to the reaction you already know from first semester for converting alcohols to alkyl bromides, because Pdr3 will do that as well. But then also somewhat analogous to the reaction of carboxylic acid to dihydrochloride. So let's take our carboxylic acid. And Pdr3. Think about how those are going to react, and using as our analogy. Let's say it's an ordinary alcohol. With this lower reaction mechanism you should already know. Last semester, which I recognize doesn't mean you do actually know it. They help me to maintain that you should. So how does an alcohol react with Pdr3? Because if an alcohol reacts that way, carboxylic acid probably also reacts that way.
I'm thinking of the boron thing where it like ends up forming a ring, but I don't think that's right.
Boron has an unfilled octet here, which means it can get attacked by things to form a negatively charged intermediate. Phosphorus has that little pair, so it doesn't behave like bromine exactly.
Okay.
But you do have 3 electron withdrawing bromines on there, which are making a significant partial positive charge on the phosphorus.
Oh, so can the oxygen of the alcohol attack the phosphorus?
The SN2 reaction. SN2 reaction at phosphorus. Or that. And kick out bromide. Which I have to coincidentally draw it right here for a good reason. What's the next reaction?
Can the bromine snag that H? No. It cannot.
This is another SN2 reaction. That part. Because the HOBr2 is really removed. And this inverts the stereochemistry, not that that matters, but it does. So two successive SN2 reactions. An SN2 reaction at phosphorus is a tetraethyl phosphorus, and an SN2 reaction at carbon to kick out the good medium group, the dibromide of phosphorus acid. So using that as our guide, what do you think is going to happen with carboxylic acid?
Can the oxygen, I feel like it would be the double bonded
It
oxygen
would
that
be
would
double bonded oxygen. Because
attack.
that's the one that has to make a charge on it. Right? This oxygen actually has a partial positive from one of the resonance structures. So it's the double bonded oxygen kicking out or reacting at phosphorus. So kick out bromide, but it's still an SN2 reaction in phosphorus. And it kicks out bromide. Okay, strategically drawn there. What's the next step? When in doubt, draw the minor resonance structure.
Will it attack the carbonyl carbon?
It will attack the carbonyl carbon because there's positive charge on it in this resonance structure. So this step is not an SN2 reaction. Notice that the net effect of those two steps is a nucleophilic acyl addition, where we've added the elements of Pdr3 across the carbonyl bond. We got the phosphorus attached to oxygen, the bromine attached to the carbon, but we've basically done a nucleophilic acyl addition. On two steps. Pretty common, right? The Lewis acid, Pdr3 is Lewis acid, gets attacked by the carbonyl carbon, and then the nucleophilic bromide comes in and attacks the carbonyl carbon. This is still a pretty good leaving group, even as Pbr2O minus. So that oxygen can come in and actually distribute it. And then it's just a simple acid-base reaction. Generating the acid bromide and Pdr3. So it's 4 steps instead of 2, because it's happening at a sp2 hybridized carbon. But it's an SN2 reaction in phosphorus, a nucleophilic attack in step 2. Then the loss of the leaving group being pushed by that extra oxygen and the proton transfer. But the net effect is to substitute an OH group for a Br, just like the net effect in this one is to substitute an OH group for Br, and the other product is the same as HOEBr2. So 4 steps in stage 1. Why do we even need to do stage 1? Why can't we just make the enol of the carboxylic acid? Because there's no way you're taking this hydrogen off in the presence of that hydrogen. Right? We need the enol because under acidic conditions, it's always the enol that's the nucleophile. You can make the enol of the acid bromide because now we don't have any hydrogens more acidic than these. And these hydrogens are actually more acidic than the same hydrogens would be adjacent to a ketone carbonyl because we've got the electron withdrawing bromine. So now we need to do a keto-enol tautomerism. And actually, if we wanted to, we could have intercepted that protonated material because in the first step of the tautomerism, we're going to go back to that intermediate. And now instead of taking the hydrogen off the oxygen, we're going to take the hydrogen off the carbon. So we're protonating at oxygen, and we're deprotonating at carbon. This is exactly what you do in any other keto-enol tautomerism. Right? This would have worked if it was a ketone. I could have done the same thing. Some kind of acid catalyst. Protonated oxygen. Deprotonated carbon. You know how to make an enol. You know how to make the enol of the acid bromide. Because it's just protonated oxygen and deprotonated carbon. So 2 steps. So 4 steps in stage 1, 2 steps in stage 2 to generate the enol of the acid bromide. And it's under acid catalysis because Pdr3 is an acidic reagent. Stage 3 is actually pretty simple. Stage 3 is basically just an alkene addition reaction. Where we are using this pi bond as a nucleophile. That's bromine. And that's a resonance stabilized carbocation. You can draw resonance structures that have a pi bond to the oxygen or a pi bond to the bromine, since both of those have lone pairs on them. Which means you don't go through a bromonium ion in this case. We don't use that 3-member ring bromonium ion because this positive charge is stable enough to happen. So we're doing a nucleophilic attack on bromine. And then we're taking that proton off in our base. And And in the absence of any better base, you could use bromide, even though that's not a very good base. So stage 3 is also 2 steps. Nucleophilic attack, followed by decarbonation. 4 steps in stage 1, 2 steps in stage 2, although you could intercept the intermediate after stage 3. If you're showing the whole mechanism, the intermediate after step 3 in stage 1 is the same as this intermediate. And so you don't really need to take the proton off and then put it back on, unless you're thinking of this as a stage reaction, in which case you want to finish stage 1 and then do stage 2. And then stage 3, bromination. We could go past followed by deprotonation. In stage 4, we can, once again, if we wanted to, intercept this intermediate. If instead of deprotonating that intermediate at oxygen, we were to do our nucleophilic attack, you would go into stage 4. We use HBr, but it could be the Pdr3. In stage 4, we're going to regenerate that carbocation, or that protonated carbonyl. This time I'm showing the resonance structure that has a positive charge on the oxygen and the double bond. You'll recognize that that's just a resonance structure of this. Instead of deprotonating that, it could get attacked by the oxygen of carboxylic acid. Remember that oxygen of that carboxylic acid is what attacked the Pdr3 in the first place? Attacking it with this carbonyl oxygen, this is a positive charge here. So it basically just added the elements of the carboxylic acid across. So I take this proton off now, using whatever base is present. And control my because that's basically just a nucleophilic addition, acyl addition of the carboxylic acid. Across the double bond of the acid bromide. So I've protonated, I've attacked with the nucleophile, and then I've taken that proton off. would have added the carboxylic acid across the pi bond. This is a six-membered ring here between this oxygen and that hydrogen. So it could easily transfer that hydrogen. And in so doing, we kick out that bromide. So you notice you're kicking the bromide off one carbonyl group, but then it can be right there, where it can add to the other carbonyl group. So we basically just switched where the HBr was, right? There was an HBr added across the left-hand carbonyl group. Now the HBr is added across the right-hand carbonyl group. The intermediate looks fairly similar, but now we've got the bromine attached where we want it. All we would have to do now is to take this carbonyl group, pull off that hydrogen, form the carbonyl group here, and then kick this back. Okay, that's a six-membered ring transition state. Favorable to aromatic. Aromatic transition states are always favorable. So stage 4 has 6 steps. Bromination, nucleophilic attack of the carbonyl on that, the one carbonyl oxygen on the other carbonyl carbon. Deprotonation to generate a neutral intermediate here, right? Effective nucleophilic racial addition. And then we're going to move that proton from one carbonyl oxygen to the other. We lost the bromine, add the bromine back, and then go through the six-membered ring transition state. You'll notice this is also a six-membered ring here. Anytime you have a six-membered ring, that proton transfer becomes favorable. So stage 1 is 4 steps. Stage 2 is 2 steps, but you can intercept that third intermediate from stage 1 and just take it directly into stage 2 if you want. Stage 3 is 2 steps, and stage 4 is 6 steps, but you can also intercept the intermediate after the first step of stage 3 and just take it directly into stage 4. So it's 14 steps if you do each stage separately, but you can make it 12 steps. I think maybe you can make it 10 steps. I think you can make it 10 steps by skipping the protonation and then deprotonation at the end of stage 1 and at the end of stage 3. So it's a lot of steps, but it's reactions you've seen before. This is all equilibrium. I hope I showed it all as equilibrium, and it's driven forward by the fact that this is the less reactive acid bromide. This is the more reactive acid bromide. So that's why the reaction ends up where it does. Right on time, except that that clock's slow, so not quite on time. And that's it. We're ready for the exam. At least I'm ready for the exam. You ready for the exam?
Ask me in a week.
In a week? Oh, you don't want to have it tomorrow? Emily wanted to have it today. She was all excited about having the exam right now.
Oh, God.
I would be ready today. I don't know why I thought it was today, but it was a mess this morning.
You probably didn't know the Hoffman rearrangement, the Hell-Vollhard-Zelinsky reaction. We hadn't covered those yet.
No, I didn't. But I was ready. I was up at 7:30. I was like, okay.
You were up early, ready for the exam. Do you have a class after this?
I do not know.
So you don't actually have to get up at 7:30 if you don't want to, because we can go long. You can go from 8:30 to 11:30 instead of 7:30 to 10:10 if you want.
All right, thank you.
Emma doesn't have that option. You have a class. You'll have to get up early. Oh well. Where that job went. The whole Hell-Vollhard-Zelinsky mechanism is kind of a pain in the ass. It's a lot of steps. It's a lot of steps.
Will we get points on the mechanism if we just know the stages?
But if you just know the stage reactions and the intermediates, but you can't show the mechanism, you get partial credit.
Okay.
I mean, if you know the mechanism for stage 2 and stage 3, but you don't know the mechanism for the other 2 stages, you get even more partial credit.
Okay. So then I just take the L on this one, because there's so much other mechanisms to memorize.
You also have to ask yourself the question, if I put this on the exam, how much time is there for other questions? Because this one would take forever to write out.
That's true.
Oh, so you're not going to put this one on the exam?
Well, what's the likelihood?
So then why did we just spend an hour on it?
What's that?
Why did we just spend an hour on it?
See, that was my thought process. I'm like, if he's showing this to us, he's...
Because these mechanisms are analogous to other mechanisms, right? So you should be able to figure out the mechanism based on previous knowledge by saying, oh, yeah, we've done this before. We've protonated the carbonyl and then attacked it with something, right? We've done this before where we've had 6-membered ring transition states that are favorable, where you can do that internal proton frequency. So.
Well,
I can't test you on everything we've covered because there's way too much stuff. I have to be judicious in my choices. But that doesn't mean you shouldn't be able to do it.
I'll still study it.
Stage 1 is kind of important because stage 1 is how to make an acid bromide from Pdr3 and a carboxylic acid, which I didn't cover back when I told you about that reaction. So here's the mechanism now.
Yeah.
Why is it always so cold in this room?
It is always so cold in this room. Even in the summer.
Huh?
Even in the summer. It's cold in this room.
Is it just this? Like, I know the science center is typically cold, but like...
There's a lot of fresh air transfer in the science center. And the buildings and ground guys explained this to me one time, why even in the summer, it's more energy efficient to have this room cold. They have to cool the air to something like 45 degrees just to get rid of the humidity, and then warm it back up to whatever temperature they want the building to be at. So even in the summer, they're cooling the air down to 45 to get rid of the humidity and then warming it back up. The more they warm it back up, the more energy it costs.
Oh.
It's not like your home system where keeping it hotter in the summer saves energy because you're not actually dehumidifying the air. Here they have to dehumidify the air anyway, so even in the summer they're heating it back up after they dehumidify it.
Nice.
Now it makes sense why it's always fucking freezing in here in the summer, and you think, surely you're wasting all that energy cooling it. Well, they're doing it anyway.
Bing.
Yep, so it's always freezing in here. I didn't press the moon and stars button on my way in. The little button on there that has the little moon on it. If you press that button, it supposedly takes this temperature up for like 2 hours.
Wait, this?
Yeah, there's a little button that has a moon on it, like a crescent moon.
Uh-huh.
Yeah, if you press that, it's ordinarily set to like raise and lower the temperature depending on whether this glass is in
It's
here.
not 70 in here.
But if you come in and you press that button, then it takes it up to there's class in session temperature. So if we come in at like 6:30, press that button, it'll warm the room up a little bit.
Huh.
It is actually, it's not that bad in here. 70 seems like a stretch, but it's not as cold as it can be.
Well, yes, of course, but it's still chilly.
It's fairly pleasant. Of course, I've been walking around up here. You've been sitting there.
Yeah.
Well, have fun with those calculations.
Well, I did most of them just right there.
Now that you've got the right
My-
substances and the
my
reaction in the right
second
direction.
KEQ was like 12 point something.
Yeah, that sounds like a reasonable number.
And the first one was like 200, but that makes sense.
Yep. Because if you look at the experimental data, isn't your equilibrium constant like 4?
Yes.
So 12's off, but it's not ridiculous. You know, it's not.
It's not magnitude.
With the
off.
PM3 number, it's quite a way off, right?
Yes.
The PM3 numbers, I think, predict like 99.6 to 0.4 as the ratio at the end,
Oh.
something like that. The DFT is a little bit better. It's still predicting a ratio that's way different from what we actually get, though.
Okay.
So neither method is a very accurate predictor.
But at least it's not like 10 to the negative 140.
10 to the negative 140 would be a number that makes no sense at all.
That's where I quit. and said
It
this
should
is
not have been that, especially with the 6-methyl being the major product.
Oh well, it's fixed now. Alright, well I'll see you on Tuesday.
Yeah.
Wow.
Well, or on Sunday for the review session.
I'll probably be here.
Of course you will.
Huh?
Of course you will. You're an overachiever. You can study by yourself, but you'll come to the review session.
Correct.
Emma will probably come to the review session. I don't know about anybody else. I think Shelby's actually home this week. I think she just decided to do her classes remote since it was Bishop breaking this goal for the whole week.
Oh.
And she said something yesterday about, after we were talking about the lab report, she said, "I'm going to go walk my dog." I said, "You're not on campus, are you?" All right. See you later.
See